So today, the key thing is that the products that are produced or obtained are liquids. So those are not gaseous products and by liquids, I think this could be like liquid fuels. Most of them are also similar to that. So short introduction about these liquid fuels, then few slides about the Fischer-Tropsch synthesis, and then the same for methanol synthesis process. And all the materials are in the articles, so or let's say 95% of this, what I show you, can be found in those two articles that are included in the section number 5. So this is just a short highlight, or I pinpoint certain things. So I recommend you to read those articles. So basically, liquid fuels, we already a little bit addressed that. So what are they interesting, and so on. I have one slide later on, but basically here in this picture that we had in the first class, so where the liquid fuels emerge, so it's basically in this carbon dioxide electrolyzer to synthetic hydrocarbons. So here is possibility to make liquid products. The second is this Fischer-Tropsch secondary conversion. So if we produce carbon monoxide, hydrogen, we can use the Fischer-Tropsch chemistry to make liquid hydrocarbon products. The methanol synthesis is not directly included in this scheme, but in principle it can be here when it's mentioned the synthetic hydrocarbons, so carbon dioxide electrolyzer. So there, that we looked, I think, in already earlier a little bit. But this is just how it links to this scheme that I have used in or shown in, let's say, nearly every within the beginning of nearly every section that we have gone through so far. And this is taken from the first article. This picture, it has quite small font, but probably you will see it. So what there is, so on the y-axis there is volumetric energy density. So basically how much energy per volume can be stored in that particular chemical or technology. And then this x-axis is the gravimetric energy density. So how much energy per kilogram. And the best applications are on the upper right corner, of course. They have the most energy per mass and most energy per density. And let's say the least good or interesting fuels are on the lower left corner. And here, if we take a look at, so generally the battery technologies, here are different batteries. So they tend to have quite low volumetric energy density and also quite low gravimetric energy density. Then if we go to the right lower corner, so here are gaseous fuels like hydrogen and methane. So they tend to have a lot of energy per kilogram, but in principle it requires quite large volume, so therefore they have this volumetric energy density is pretty low. And if we want to combine the good sides, or if we want to have high both, so then we are ending with different types of liquid and solid fuels. So basically in terms of energy density, so these are superior. If we talk about current diesel, gasoline, or then these products that we, for example, make in this power to liquid processes. So methanol, dimethyl ether, or natural so this is liquefied natural gas. That's not directly comparable, but if you have a liquid fuel, so it by nature has quite high energy density by both of these measures, by volume and by mass. So that's why the liquid fuels are quite interesting. And there are this speculation still that like liquid fuels remain the main source for energy. Let's say if we talk about aviation, so airplanes are filled with kerosene still for several decades to come. So it's not visible that in the near future it could be replaced by some battery technology or something like that. The same applies for heavy duty trucks and traffic. So there the diesel type fuels are superior if we talk about long distance transport and such. And at least those are, let's say, sections that are hard to replace with other types of energy sources. So there, these fuels have high importance still in the future. Of course, if the batteries are good solutions, so you use it there where they are the optimum solution, but in this aviation and transportation, so these liquid fuels are still difficult to, let's say, compensate or replace with some other energy or fuel alternatives. This graph is also from that chapter article number 15. So basically there is nothing that special, but if we think about this power to liquids concept, so the idea is to utilize the green or renewable energy, apply it in the electrolysis of water, and use that hydrogen coupled to carbon dioxide in hydrocarbon synthesis, and basically then you get hydrocarbons which are often found in these liquid fuels mentioned before, like gasoline, diesel, kerosene, and that's how those are made. Here is just some arrows pointing that release of oxygen, use of water, and where the CO2 goes when it's emitted, like at this combustion stage. So of course this CO2 stored in the fuels in this synthesis stage, so it's released by combustion reaction with air. It produces carbon dioxide and water, which is the reverse to this reaction. So here hydrocarbon and water is the product. But basically this type of here also, this is not always highlighted in these chemistry related books, but this energy put into the system here from solar or wind or whatever renewable source, so it's of course released in the combustion stage, so that heats up the engine or moves the car or so. So the same amount of energy put in here is roughly released at the end of this, or at combustion stage. Here are some of the processes listed which produce synthesis gas, or type. So here from natural gas or coal or biomass, so you can gasify or use the steam reforming to make from fossil. These are coal and natural gas are fossil based, but you can end up with mixture of carbon monoxide, hydrogen. And the same applies if you use solid coal for gasification, so that you get mixture of this same, but slightly the ratio varies a bit. And biomass is this a greener version, so instead of using coal or so you can use the coal in biomass and gasify it with quite similar technology, so you end up these starting materials. But then this power to liquids processes utilize these Fischer-Tropsch and methanol routes, so there basically the technologies are not reforming and gasification, but there is starting materials, water, carbon dioxide, converted with electrolysis and reverse water gas shift reaction to make roughly the same products as in these 3 previous steps. Methanol synthesis utilizes water and carbon dioxide as the Fischer-Tropsch one. There is the electrolysis, the similar electrolysis producing the hydrogen, but then carbon dioxide can be made with it's not made by water gas, but the actual methanol synthesis step. And then it can be reformed still further to HC. This refers to hydrocarbons, so hydrocarbons. So there are these two pathways from Fischer-Tropsch and methanol, and the difference relies in the second step. So in that, I have better pictures about this in the next slide. But the intermediate product in these processes, so it's carbon monoxide in the Fischer-Tropsch and it's methanol in the methanol pathway. And there are slightly different approaches, so-called direct and indirect way of utilizing this Fischer-Tropsch to make these products. The traditional fossil-based Fischer-Tropsch route is based on hydrogenation of carbon dioxide in this indirect method, which basically utilizes the water gas shift reaction. And there are 2 steps, so reduction of CO2 to carbon monoxide, and then hydrogenation of that formed carbon monoxide. And like the name says, so this is indirect, or it kind of has two different reactions or steps. The direct, it happens in a single conversion step, or at least in a single reaction step, not in a different reactors. This graph is also from the article, just copy pasted. It's missing this number 15 in the beginning, but here is Fischer-Tropsch pathway and indirect and direct steps. So in both, so the products are similar. So liquid hydrocarbons, which are basically components in fuels. So the indirect step contains separate hydrogen production by this electrolysis and some kind of CO2 capture we have covered many of the sources, so there are several places where you can get CO2 captured either at very high concentration levels or at very low concentration levels. But these are fed into this water gas shift, and you notice that this carbon dioxide disappears or reduces notably, so you end up with mixture of water, carbon monoxide and hydrogen, and these go into the Fischer-Tropsch reactor and react to hydrocarbons. Here in the direct step, so there is not this separate RWGS, so reverse water gas shift step, but these both ingredients are fed into the Fischer-Tropsch reactor. And if you wonder what are the differences, so these are explained in the articles. So if you take a look at this, so you find more of conditions, catalysts, reactants, reactors, and things that are used for these different steps. The same for methanol, so there is the indirect and direct way, and they slightly vary from each other. Indirect is that we already little bit, or I mentioned this, so you make methanol from carbon dioxide over the catalyst, and then it's converted into these desired hydrocarbons with another catalyst. Direct conversion is basically direct, so there are the reactants, and it's converted straight to this water methanol mixture. I think I have that, yes, here. So the difference is very similar, like in that FT, so Fischer-Tropsch route or pathway. So in basically both schemes, so there is the same electrolysis of water to make the hydrogen needed, and also to utilize some kind of carbon dioxide, CO2 capture to concentrate or get the carbon source for the synthesis. And these two are the ingredients for methanol synthesis, and then it can be still processed further into these desired hydrocarbon products. The same initial step here, but it goes directly to liquid hydrocarbons. So slightly simpler, but of course this simpler process is desired in practice, but it's not maybe that efficient, or it's more difficult to realize with high conversion, high selectivity, and so on. But these two alternatives exist. I think I already mentioned this. This is totally the same as it was here. Okay, maybe I will say a few words about this Fischer-Tropsch synthesis still. So this is from the article 15 also. So just the same things in a maybe in a different scheme type presentation. So this is just a present kind of proposed mechanism for what happens there, but of course this is very general. So the reactants are here, and the water gas shift produces the carbon monoxide out from the mixtures. So then it's good for the Fischer-Tropsch that basically makes the desired products. Then water is removed, and then unreacted reactants are recycled upstream in the process and used or reused again in that synthesis step. But I recommend to take a look at this article, because there is not only the pictures, but there is also the chapters and the text that explains this, what happens in each part in much more detail. This also comes from the article, so this is some kind of chemical reactions that take place in this Fischer-Tropsch mechanism. So the water gas shift reaction is here. So CO2 and hydrogen react, and they produce carbon monoxide and water. And of course, this shift is basic. This is equilibrium driven reaction, so that if you adjust the temperature and pressure, so you can boost a little bit the equilibrium, I suppose. Then what happens in the Fischer-Tropsch reaction is that these formed products from that water gas shift basically polymerize into longer chain hydrocarbons. We haven't covered the Fischer-Tropsch chemistry during this course, but it's kind of it resembles the polymerization reactions, like that there is this kind of monomer units being, like the CH2 building blocks are put or connected into longer chains in that reaction. This describes the overall reaction, which is kind of result from these two different reactions, or those are added together. So starting material makes hydrocarbons and water. That's the outcome from this. There is a lot of information about different catalysts in the articles, so you don't need to know those in very detailed fashion, but it's good to have some kind of idea. So these catalysts are so-called heterogeneous catalysts. So those are solid catalytic materials, and these chemical reactions happen on the surface of these catalytic materials. And like listed here, so the active phase where the chemistry takes place, so these are certain metals. So the iron-based catalyst, this could modify the text. It looks a little bit strange, but the iron-based catalysts are slightly better for this purpose in this context, while this, which are used also in Fischer-Tropsch, so cobalt, nickel, and ruthenium promote slightly different reactions. But it's maybe enough of that. Okay, now I will have a short break and then we finalize this slides. So we'll have a 15-minute break and then I'll continue with this methanol part.
Okay.
So let's continue. I will say a few words about the methanol synthesis process, something about the products and applications and so on. And I think this is majority of this material again comes from the course articles that I have included. So article number 16, I think, is for the methanol synthesis part. The reference material or source for the data. And methanol has a long history, and conventionally and still it's made from coal and natural gas. So basically it's a fossil based process which makes the methanol, let's say, a fossil material, if you like, in that way. So roughly 100 years ago, the first commercial plant came in operation for making of methanol, and this current process that I also showed you earlier The catalytic process started in late 1960s, so it's already quite established and old in that sense. And of course, it has been optimized in multiple ways in terms of process, catalytic materials, and various things for the natural gas and the coal. That is the main raw materials used still today. And basically, it's fairly economical as all of these, let's say, large-scale oil refinery or petrochemical industry processes that have a very long history of optimization and improvements in the different steps of the reaction. So let's say that if this has been improved for 70 years already, the process, so it's certainly very fine-tuned for different parameters and properties compared to these power to liquid processes that are fairly new ones. So I think oldest ones can be 10-15 years old. So of course those are not so optimized for the competition yet, but are coming. Here are some products that can be made out from methanol. So in the beginning, I already presented some, let's say, properties that make methanol interesting as a primary product and as a reactant for secondary products. So here are a few examples. So basically methanol, so it's a simplest alcohol. So you can make ethers, so dimethyl ethers. This can be used as a fuel. And in regular, these ambient temperatures, it's kind of gaseous material. So this is not purely liquid, but if you slightly pressurize it, so it liquefies. And this DME can be converted to olefins, which are then important raw materials in for example, making, or can be raw materials for making different types of plastics and polymers. Also, methyl acetate, a basic chemical, can be made out, and this would be acetic acid. So with hydrolysis of the ester, so you get a acetic acid as a product. Can also get straight from methanol, the acid. And here this is ethanol, so the second simplest alcohol, so it has one more carbon compared to the methanol itself. Also, MTG, methanol to gasoline, so you can convert in this process methanol to hydrocarbons. So this kind of makes methanol a versatile chemical. It's an energy storage and it's a starting material for many chemicals. So that's some aspects or answers to this question, why methanol. Here are more. So why methanol and why power to methanol processes? So this power to methanol is according to some studies, so it's more feasible economically than the power to methane, what we discussed last time. So it's beneficial to make methanol instead of methane. Methanol, as you saw already, so it's an intermediate that can be processed to other fuels and chemicals that are quite valuable, or there is a big demand for such kind of chemicals. This is maybe doesn't answer to this question, but according to this article, so price of methanol has consistently increased. And as a fuel, methanol has very high energy density compared to these gaseous fuels like hydrogen and methane. So that's what we looked in the very first slide, more or less, that is energy densities of different types of fuels. Also, methanol can be used as such as a fuel in fuel cells, or it can be reformed to hydrogen. So you can reform methanol to hydrogen, or there are also methanol fuel cells that you can use. Basically, the alcohol feed it straight into the fuel cell. So this is just some background behind, like why methanol is maybe interesting, and also that some applications of it. This is article number 16. I have multiple times referred to that. So the explanations of these can be found in there, but these are different, like here is the actual chemical methanol synthesis. So these few slides represent different upstream alternatives. So this is the one alternative for making methanol. So this captured CO2 and electrolysis product produced hydrogen are compressed and fed into the methanol synthesis reaction or reactor or process. But here are several other alternatives that can be also done. Basically, all these alternatives result in the very same methanol product. So just describes that there are some variations or tiny variations what you can do. So the top one here is the same that I showed you. So now this is the A, so the first. Then here are B, C, and on this next slide there is D, E, and F. So different combinations. So aqueous electrolysis and electrolysis of carbon dioxide. So that's one possibility. You get hydrogen and carbon monoxide. So those were the raw materials in the, let's say, this traditional methanol synthesis. Or no, it's this synthesis gas raw materials as well. But here's the second alternative is high temperature gaseous or co-electrolysis. So there is carbon dioxide and water processed together. So then here is third alternative, electrolysis making water, carbon monoxide fed separately to this water gas shift reaction, and those products end up in the methanol or make the methanol synthesis. Or there is just a co-electrolysis and can make methanol from those ingredients as well. Here is the last fifth possibility, electrolysis and water gas shift, and complete the methanol synthesis from those ingredients. Just like that there are if you use these coarse materials, so there are like variations in these techniques. There are tens or several articles describing, let's say, methanol synthesis or power to methanol processes. So just pay attention that not all have the total same flow scheme or totally same conditions or chemistry perhaps. So there are variations. Some are better, some are maybe more suited to something else, and so on. This is nearly the last slide. So again, from that same article, so it just describes some of these methanol synthesis processes. So here in the left-hand side, there is the source for different ingredients, energy, and so on. Then here in the middle, there is the different production processes and also what products are obtained, but it tells maybe if you follow the arrows some of these connections between different processes. So here you'll see gasification, reforming, CO2 electrolysis, co-electrolysis with water and CO2, and then just the water electrolysis. So these are some kind of summarizing those previous slides or previous 5 different methods all together. And also in that second step, so here you see these are the opposite reactions. So this is reverse water-gas shift, and this is water-gas shift reaction. So slightly different chemistry takes place. But all the arrows are ending to the methanol synthesis, which basically produces the very same methanol. So the information is the same as in here. So methanol is always the product, but the upstream units and unit operations vary a bit. And then there is still the purification, where basically water is removed, so the methanol alcohol is more concentrated and can be used, like it becomes the, for example, fuel grade methanol. And that's the information from this slide. So there are multiple options how to make the very same product. That is very often the case in organic chemistry or when making hydrocarbons. So you can start from different raw materials and end up in the same end product. Of course, the chemistry and the steps are different, as is in this picture as well, but the one product can be made out from different raw materials following different chemistries and processes. So the end message is that methanol can be produced with various methods in this power to liquid, under this power to liquid concept. We went through those briefly already. And then this product can be further transformed into various products. And also here I copied a list of some commercialized processes. So there is a methanol to gasoline process by Mobile. Then Haldor Topsoe has made also their own version for Topsoe. Methanol to olefins process exists, so it uses methanol to make olefins. Olefin is a component which has carbon-carbon double bonds, one or several in principle, but those are useful raw materials, for example, for making polyolefins, which are like plastics, polyethylene, polypropylene, and many other alternatives. Then there is the methanol to propylene process also. So this is also an olefin propylene, but specific. So 3 carbons, the olefins are more general in this bullet number 3. But those are the things related to methanol. And